Hello everyone, welcome to 1045 Engineering. I'm here with yet another video in Grind 75 or Better Blind 75 coding series. So let's look at today's problem. So today we are going to perform coding question on balanced binary tree. Okay, so given a binary tree, we have to determine if it is height balanced or not. So just to give the prerequisite, a height balance is a tree where the difference in the depth of its two subtrees is never more than 1. So if you want to understand from this case, here for 3, height of the left subtree is 9, height of the right subtree is 2. 1 here and 2 this one, right? So it's not more than 1. But let's say 15 had one more child, okay? Then the difference from 3's perspective, on left hand side it would be 1 height, on right hand side it would be 1, 2, 3, and it wouldn't be balanced binary tree. Okay, let's jump to the problem statement. Okay, in the Grind 75 list we have come a long way by now. Earlier in last video we finished lowest common ancestor of a binary search tree. You can watch that video. Let's go through balanced binary tree. Okay, so yeah, we are given this tree. We have to check if it is height balanced or not. There are different approaches that you can use. The simplest ones, we'll go with the simplest one first, and then we'll see if it is not good enough, we'll go with a better approach as well. Okay, yeah, just to see, for this case, this is not height balance, right? Because if you look at from the root node 1, right subtree has a height of 1, but the left subtree has a height of 1, 2, 3. It's not height balanced. It would be height balanced if the height difference between the two subtrees is not more than 1. So if left hand side height is 3, right can be 2 or 4. Okay, let's start. So let's start with the base conditions. By now everyone is aware how come base conditions are so important. So we'll write a base case. If the root is null, it is height balance, right? It is height balance by definition, right? Because if root is null, its left child, right child both are null, and their height difference is not more than 1 since both of them are null. So we can simply say if root is equal to null, will return true. Now what we want to do is we want to recursively check for the height of the left subtree and for the height of the right subtree. Similarly, after 3, when we come to 20, for 20 we check the height of the left subtree and height of the right subtree. So we have to recursively check it. Okay, but this one thing is for sure, that we need a function to check the height, right? So let's quickly create a method to check the height of the binary tree. Public int height, whatever it is passed to it, tree node. So this tree node is this one and this one. That's the data type. Tree node root will say, again it will have a base case. Let me write it quickly. Base case, if the root is null. So if the root is null, what is the height? Yes, height is 0. So we'll simply check if root is equal to null, height is equal to 0. Clear? And recursively, how will it find out the height for 20? If 20 was null, it will return 0. But if 20 is not null, height of 20 can be found out by finding the height of left subtree, finding the height of right subtree. Whichever one is more, add 1 extra for 20. So 7's height is 1, 15's height is 1. For 20, max of them is still 1. 1 plus 1, 2. Height of 20 is 2. Height of, if we consider the height from 3, height of this complete tree would be max of left hand side and right hand side. Left hand side is 1 height, right hand side is 2 height. So 2 and plus 1 for this current node. So 3. So we have to find the height of left subtree, right subtree, and add 1 extra into whichever one is greater. Okay, I'll simply write it. So we are going to check recursively calculate the height. By recursively it means the calls internal the calls. Recursively we'll calculate the height of the tree as the maximum height of its left and right subtree plus 1 for the current node. Right, it's clear. So we can simply say return math dot max is the operation to find out the max between two numbers. So we are going to return the maximum of two heights. So we'll call the height function again, HEIGHT height. I'll pass root dot left, right, and then again call height root dot right. So math dot max is going to return whichever height is bigger, whether root dot left height is bigger or root dot right height is bigger. Like if you were at root 3, root dot left height would come out 1, root dot right height would come out as 2, and then we will simply add 1 to it and return. This way we will have 3 height for root 3. Okay, this is a very simple operation for calculating the height. So now let's come back to our main method, which is balanced or not. So we checked if the root is equal to null, return true, right? Now what should we check? We should check if height of left subtree and height of right subtree are balanced or not, if the height difference between them is less than equal to 1 or not, right? So let's quickly check this. So check if the height difference of the left and right subtree is not more than 1, because if it is more than 1 it is not balanced, it's not height balanced, right? That's as per the definition. If you see here, binary tree is a binary tree in which depth of two subtree of every node never differs by more than 1. Okay, so we'll check boolean as a flag, is height balanced. Okay, and we'll check math dot absolute. So math dot absolute actually gets us the value even if it's negative or positive. So -1 is 1, -4 is 4, +4 is 4, +1 is 1. Okay, so first calculate the height of root dot left and then minus height of root dot right. So if we are at 3 with root dot left, we are trying to calculate the height of this left subtree, which is 1. Height root dot right, we are trying to calculate the height of right subtree, which is this area. So height of right subtree is 2. 1 minus 2 is -1. Math dot absolute of -1 is 1. So the height difference between the two subtrees is 1, right? Correct, right? Now we have calculated the height, it is 1. We'll just compare, is this less than or equal to 1? Because if both the height are equal, it is a balanced tree. If the height difference is 0, it is a balanced tree. If the height difference is 1, it is a balanced tree. So we are simply checking whatever is the height difference, if it is less than or equal to 1, and we'll simply put true or false in our is height balanced variable. Clear? So by this we know, okay, this is height balance, this is height balance. Now we will recursively check, right? I'll say check recursively if both the left and right subtrees are balanced. So we found the height difference. With this we'll find the height. Okay, left side subtree height is 1, right side subtree height is 2, height difference is not more than 1. So this node is height balance. But it is height balanced if all the nodes follow this formation. It means it cannot happen that 20 now has more children on this side and that side. So let me show you example like this just to make you understand. Let's say on the first one we have 3, it has 2 children, 9 and 20. Now 9 has 2 children, that is 1 and 4. 20 has 2 children, that is 15. Let's consider 20 has 2 children. 15 and 7. Let's consider only one child for 9. Okay, and then 1 also has another child, let's say 3. On this side it has 20, 15, 7, and 15 has child as 8. Okay, now 9 has 1, 1 has 3. 9 left side subtree is not height balanced, but the height of this left subtree will come out as 3, height of the right subtree will come out as 3, and this top 3 will look like height balanced. But it cannot be height balanced if 9 has a child 1 and that 1 has a child 3, because then internally 9 itself is not height balanced, right? Because its left hand side has 1 and then 3 below 1, and right child does not have anything. So difference is 2 for 9. So we checked the height difference from the root node. Now we want to check whether they are recursively height balanced themselves or not. So now we'll check for individual left subtree and the right subtree. So we'll say boolean left balanced is equal to, we'll call, what's the spelling of our method, is balanced, right? We'll call this method again is balanced. We'll pass root dot left. Similarly, boolean right balanced is equal to is balanced root dot right. Okay, so with this one we checked for the root that we calculated left subtree height, right subtree height. If it is not more than 1, the difference is not more than 1, then yes, it is height balanced. But then we also have to check it for the left subtree completely, if left subtree is height balanced or not. So we recursively call is balanced method and check for root dot left. Similarly, we call is balanced method and check for root dot right. In the end we are going to simply say return if the root is height balanced and it is its left subtree is balanced, so is left balanced, and its right subtree is balanced, so is right balanced. So if all these 3 variables are true, we are going to return true, that our root is balanced. Otherwise it is going to return false if either of the left subtree or the right subtree is not true, or either the height in itself is not true. So if 3 in itself is not true, right? Actually, if this loop is false, you can directly return from here as well, because if the parent root only is not height balanced, no need to check for the left subtree or the right subtree. Okay, let's run. In the meantime, I would we are facing some errors. Spelling mistake. Line 24, HEIGHT. Okay, run. It's taking really long. Okay, yeah. Cannot find symbol, height equal to 0, line number 37. Oh, sorry, I just mentioned it like height is equal to 0 in this height. You just simply say return 0. Oops. Let's look at the solution. Okay, in the meantime I would say please tell me what do you think is the time complexity of this algorithm that we are using. Okay, we beat 5.07% of the users with Java. That is actually not a very good solution. We are going to improve upon it. Yeah, still the same. Yeah, but do try to understand what is the time complexity for this algorithm and do let me know in the comment section. Okay, now let's take a better approach. We have already solved with this approach. It works. Okay, in most cases it works. It's working fine. In all the cases it would work, but we need a better approach. We need something that runs much faster. If you see in the solution, firstly we are checking the height and then we are checking whether it is balanced or not. That is the only hint I am going to provide, and please let me know what is the time complexity for this solution. Let's start with our second approach. I should say reset to default code definition. Confirm. Okay. So now how will we say, let's create a method. So in one function we'll check for the height as well as if it is balanced or not. So we are going to write another method, private if I return void, no, let's return int. I'll return the value from this, check balance, pre-node root. Okay, so first would be our base condition, right? So base case, if root is null, height is 0. So we can simply say if root is equal to null, we'll say return 0. So I'll return 0 height from this method. Now if it is not equal to null, we'll say int left height is equal to, will recursively call the check balance method again to calculate the left subtree height. So int left height would be check balance and we'll pass root dot left. Similarly int right height is equal to check balance root dot right. Okay, now now we want something. So if the height is not equal, we are going to return -1 every time. Okay, and then we can directly compare with -1 and we can check the height as well as is balanced or not. Okay, so far so good. This method looks pretty simple. If root equal to null, we'll return 0 height. Similarly we'll calculate the left height and the right height. Okay, now check this method. If left height is equal to -1 or right height is equal to -1 or math dot absolute, we are aware by now that what is absolute, left height minus right height, है ना? So is greater than 1. So if the height difference between two subtrees is more than 1, that means it is not balanced, right? So we are going to return -1. So if left subtree height is more than right subtree height by 1, so if left subtree height came out to be, let's say 4, right subtree height is 2, 4 minus 2 is 2, is greater than 1, we are going to return -1 from the recurring method. In turn, what will happen, either one of the subtrees will get a -1 height, that is, let's say, right, for this case, right, for the earlier case we were considering, so 9 has a child 1 and 1 below has a child 3. So 9 will get -1 as its left height. Similarly, 9 will return -1 to 3. When we are checking from the root node 3, we'll get the left height as -1. If we are getting the -1 on the left height, we can simply return -1 to 3, because even if the right side is balanced, the left side is not balanced. And similarly, we can directly check here in our main method, return check balance will pass root is not equal to -1. If it is equal to -1, it will return false. If it is not equal to -1, it is true. Okay, if it passes, if our check balance method passes this loop as well, we are going to say return math dot max. So we have to find out either of the left height height of left subtree or height of right subtree, whichever one is greater, and add 1 to it. So left height or right height. So math.max is going to find the left height or right height, whichever number is greater, and then we'll add +1 to it. Okay, simple solution. This is okay. I'll just put some comments for everyone. We'll say calculate and return height of current tree. You can actually say current node as well. Okay, so if we run by the test case, first we are at 3, we passed 3 here, we came here. 3 equal to null? No. Let's calculate the left height. We calculated the left height, it came out to be 1. We calculate the right height, it came out to be 2. Left height equal to -1? No. Right height equal to -1? No. Math.absolute left height minus right height, 1 minus 2 minus 1. Absolute 1. 1 is greater than 1? No. So it didn't come here. So then return math.max left height, which is 1, right height, which is 1, +1. So max of left height or right height is 2. So 2 plus 1, 3. 3 is returned from this case. 3 is not equal to -1, right? 3 is not equal to -1. That means it's a height balanced binary tree. Simple. Let's quickly understand for this use case where it is going to fail. Okay, so we are at 1. We check. We ask the check balance root equal to null. No. Left height, let's directly calculate it. 1 2 3. So we got 3 from the left height. Right height, we got 1. Left height equal to -1. Actually we would have received -1 here itself, because when we calculate the left height, we call the check balance again on node 2. Again 2 is not equal to null. Left height, it will be 1 2. Right height, it would be 1. Okay, so it wouldn't happen in this case, but let's say let's come back to 1. So we were at 1, we started. Let's calculate the left height. Left height came out to 1 2 3. Right height came out 1. Is left height equal to -1? No. Right height equal to -1? No. Math.absolute left height minus right height, 3 minus 1 is 2. 2 is greater than 1? Yes. Return -1. So -1 is returned back to check balance with so it is equal to -1. We are checking for not equal to, and it is equal to -1. So it will return false. Clear? Great. In case you have any questions, please let me know in the comment section. Very soon I'll put all the solutions in GitHub and update the link in the video's bio section. With this, we'll mark balanced binary tree complete. Okay. Yeah, that's all from today's video, everyone. Thank you. Have a great day. Please like, share, and subscribe.